Hi everybody. This is a overview lecture to go along with assignment 16, which is about optimization. Uh, in a sense, optimization is really the whole point of learning calculus. Optimization literally means finding optimal solutions to a variety of problems. Um, I think I just want to give you a sort of a course overview first. A real typical phenomenon for a business is to have some kind of a function that they'd like to find the highest value of. One standard thing might be profit, right? So if this was the y-axis was profit in dollars, or maybe millions of dollars, hopefully, and the x-axis was something that might affect profit. Maybe maybe this is advertising budget. Um, you're going to find generally that if you don't spend enough money on advertising, your profits won't be at a maximum. So there's really going to be some kind of a curve that looks like this in there, where as you increase the amount of money you spend on advertising, you increase the profit. But then there comes a point when you've overdone it, right? When you've spent too much money and maybe your ads are starting to get annoying. Uh, who knows? Maybe you're just literally spending so much money on the advertising that it's eating into your profits. So that's a real typical shape of a graph for a situation like this. And there's a sweet spot. You can tell that position that I put a little dot on is where you would want to be. You would want to say, okay, let's figure out the advertising budget that makes our profit the greatest. Now, in reality, there's going to be lots of different things like that. Like production level might be something that affects profit, and these things can interact. So um, the the problem is more difficult than this one, but this gets you started on the idea of finding optimal values for a parameter. So in this case, the advertising budget would be this thing you're able to adjust, and maximizing the profit is the big idea. Well, to begin talking about this process, I think first we're going to need to learn some terminology. So, excuse me, this is the beginning of section 2.7. You'll notice there is a gap in the coverage of this compendium book we've got. So there was no 2.6. We went from 5 right to 7. If you are feeling, as I sometimes am, a little confused about the page numbering, uh, this is numbered 129 because that's where it was in the book it came from, but in the combined PDF we're on page 174. See that? So yeah, so here's the important parts in this opening. They put them in these big yellow boxes. Just definitions of the words that are, or the phrases that are in bold there. So a local maximum, a function f has a local maximum at a if f at a is greater than or equal to f of x for all x near a. That um, that really requires some talking about. First of all, we say that the local maximum is actually the y coordinate, but what we really care about is the x coordinate. In my advertising budget example, you care about setting the advertising budget to the sort of right value. And while you might want to know what the actual maximum profit is, in a certain sense, it's good enough to just know that it is the maximum. Anyway, let's talk about some linguistics here. If you have one local maximum, which means a place where your y-coordinates are larger than all the nearby y-coordinates, you say a maximum. If there's several such things, and there can be, it's a local maxima, or they are local maxima. The plural form ends in a, and the singular form ends in um. So for both of these, you could talk about a local minimum or many local minima. And you may know there's a model of Toyota car that's called a Maxima. I think that's Toyota. Anyway, That's not important. That's just, it's likely that they were, hearkening back to their calculus class and thinking that's a cool sounding word to use as a car model. If you want to speak generically, and in my opinion, the book has a sort of an unprofessional sounding thing here. I wouldn't talk about a local extreme. You can say a local extreme value, that's okay, but it's better to echo the UM and the A bits that from the local maximum or many local maxima. You would say a local extremum or several local extrema. But anyway, what's an extremum? It's a place where you're either at a max or a min. Speaking of which, the next little sentence here says, we often save syllables by writing max or min. I would just advise that you not drop the modifier local here, because we care whether it's a best value for values in a small vicinity, or is it a best value overall? By the way, yeah, this is the terminology I learned, that you'll say relative rather than local. So if I slip up and say relative, you'll know that I mean that. And I already mentioned the phrase or the word optimizing. That's basically the process you go through to find maxima and minima. All right, so that's enough about the local or the relative extreme values. Let's look at the next yellow box, which talks about global. This means best overall, not just best for the values nearby. So f has a global maximum at a if the value of f at a is bigger than the value of f at x for everything in the domain of f. And similarly, you have a global minimum. Well, that means the value at a is smaller than everything else that's in the domain of f. And just in parallel to what happened with the local versions of things, we also talk about global extrema. So you can say a global extreme value. I don't think just saying a global extreme is correct, to be honest, but you could have a global extremum. You can have multiple global extrema. Usually you have at least a max and a min, so you have those two, but sometimes there's a tie. In fact, it's possible you have multiple global maxima and multiple global minima that are the same value. So lots of global extrema. All right, well, I think that's the main point of the terminology we wanted to talk about. Let me bring up a GeoGebra window. Oops. Yeah, cool. This is I didn't entirely randomly create this graph, but the idea is just sort of a quasi-random graph anyway. I wanted to show you something that's representative of the phenomena that we can have. So you can see from the formula involved, it's a cubic, and then there's quadratic and other terms in it. And I've also specified the domain. So you see how the graph only extends from x equals 0 to x equals 6. We've got a limited range. I shouldn't say range. It is domain, but the span of values from 0 to 6 is all that are considered here. So when we look at this particular graph, you can see lots of extreme values. Should I play the, yeah, I'm going to go ahead and play the point moving along the graph. That's definitely the highest spot right there. That's a low spot, but not the overall lowest. Where is the overall lowest position? That's when you start out at x equals 0. And you've got the value is just, well, it's smaller than 1, right? So that's a global minimum, since there's one of them. Here's a local maximum. It's the biggest value for things that are nearby. If I move off of this, where is it happening? About 2.45, I think, is the actual highest value. But if I move it a little to the left, a little to the right, I go down from there. So those are, that's an indication that it's a local extreme value. But in that case, it's also the global extreme value. That's the highest spot on the whole graph for anywhere in the span of values that are allowed for its input. Backing up right to about, where is that? About there. Looks like 5.2 roughly. We've got a local minimum value. That is not the global minimum value. The global minimum value happens back over here. Now, this is a good graph to illustrate the sort of stuff we're going to need to do in calculus. If you have a local extreme value, like this minimum or that maximum right there, you can find those with calculus, because notice what's going on there. The derivative of the function is 0 right there. So you have the function, take its derivative, solve where is that derivative equal to 0. That tells you the tangent line is horizontal on the original graph there. And that's a marker for you might be at the top of a hill. I do want to point out that it's only a you might be. You can have a horizontal tangent and then take off from there. I'm not sure. Maybe I should switch over to the all me picture. So let me try to mime for you that behavior I was just talking about. Suppose you had a graph that was going up, and then it curved over and had a horizontal tangent, but then began going up again. You didn't have a max, you didn't have a min, you did have a horizontal tangent for a second. So that's something to watch out for. You will find the maxes and mins amongst the places where the derivative is 0. But there are some places where the derivative is 0 where they won't turn out to be maxes and mins. All right. So in this image, we've got, let's just recapitulate it all. There's a maximum right there. There's a minimum. This is the local sort of minimum, about there. Some folks would call that a local maximum because it's the highest value for points nearby this position on the graph. But I tend to say, look, that's the endpoint of the interval. And that's the other things that we always need to consider. The calculus is just not going to apply at the endpoints. You could, you could say as we were heading this way, we were heading downward, but you reached the left-hand limit of the area where the function is defined. And so you've got a value that's lower than anything else without having a horizontal tangent. So yeah, that's the upshot. Let's go to look at the place where I can write stuff, and we will keep track of that. Local extrema occur in sort of two ways. Whoops, I meant to say extrema, because I'm talking the plural here. Local extrema occur basically at places, we'll call A again, like they did in the book, at a value A such that f prime at A is 0. That's the horizontal tangent phenomena. There's another possibility. I'm feeling like this is not I haven't turned this into a sentence. Local extrema occur at, honestly, I would prefer to just say A, if, okay, one possibility is the derivative is 0 there. The other possibility is that the derivative is undefined there. And let me just graph for you something that would have that kind of behavior. You can have a local maximum like that, where the peak of the graph happens and everything's smooth. But you can also have a local maximum that occurs like that, where there's a point on the graph. And that's a spot where the derivative is undefined, because just to the left, we have a very high positive slope, and then just to the right, we have a very high negative slope. It's really not possible to assign a particular slope to that needle-sharp point on there. Now, these are local extrema. Of the two that I have here, this local extrema where the horizontal tangent exists, and this local extrema where there is no tangent, that one's the bigger, right? So that's your global extrema for the portion of the graph that I've drawn here. Anyway, the job essentially goes like so. All right, so this is more or less the process you go through. You're trying to find all the local, and once you've found all the local guys, you just pick out the biggest amongst them. That's going to be the global extrema, biggest or smallest, depending on which you're dealing with. So here's the process. Calculate the derivative, f prime, for the thing you're actually interested in. Figure out the x coordinates where one of two things happens. Either that should have a prime on it. F prime is 0, or f prime is undefined. Now, all the local extrema have to occur at those x coordinates you just found. And so those are known as critical points. Well, this generally means that there's a small and certainly a finite number of places where you have to check for global extrema. But point 4 is really kind of important to keep track of. You look at all those critical points, but also check out the boundary. If the function is got a domain that goes from 0 to 11, then check out f at 0 and check out f at 11 also. So look at the boundary, look at all the critical points. You will find the global extreme values amongst them, and literally the global maximum is the one that's the largest y-coordinate, the largest f of x value. The global minimum is going to be the smallest y-coordinate. One quick last thing to deal with is distinguishing between points where the derivative is 0 or undefined, but that you don't have a local extreme value, versus those where you do. This is actually fairly easy. This is a thing known as the first derivative test. So think about what a maximum value means. If you're traveling towards a maximum value, you're heading upward, right? Well, that means in this range here, f prime of x was a positive number. We had derivatives that were going in the upward direction. We reach that spot, and if we then begin descending, well, that's a region where f prime of x is negative. If that happens, if the derivative goes from positive to negative, you're at a max. If what else can happen? Well, you might have a negative derivative turning into a positive derivative. So this would be f prime is less than 0 here. I'm dropping the arguments now. And f prime bigger than 0 here. Again, we've got an extreme value. What these two have in common is the sign of f prime changed when we hit the critical point. The derivative was positive, then 0, and then it became negative. Here it was negative, then 0, and then it became positive. If you don't actually have an extreme value there, it's because you've got a graph that has this sort of picture on it. Positive derivative, 0 for a moment, but then taking off and being positive again. So that's a case where you don't have an extreme value. And upside down, that would look like negative, 0, and then negative. The signs I'm talking about are the slopes of the graphs here. But you notice how these things kind of look like x cubed. Y equals x cubed has a 0 derivative at that location, but it's not a max, it's not a min. There are values quite nearby that are bigger, and there are there are values quite nearby that are also smaller. Let's just do one last thing here in this section. I want to tell you about something that happens quite frequently in business applications. You're finding the minimum and maximum value on parabolas. Right, so if we're as we often are finding maxima and minimum on parabolas, there's a fairly easy way to deal with it. You see the maxima and minima, there's always either one or one of the other. They always occur at the vertex, because think about the shape of a parabola, right? It's either a U-shaped graph with a low spot on it, or it's upside down and it's a U-shaped graph with a high spot on it. Now, you also do need to remember to check on the boundary of the domain. If the function has a limited span of x values that are allowed, then you've got to look at the left and the right hand endpoints as well. Anyway, there's a straightforward shortcut. If it's going to happen at the vertex, well, we know the the x-coordinate of the vertex. It's negative b over 2a. That actually comes out of the quadratic formula. So we know location to find the max or min, the local max or min, and then together with any boundary points on a parabola, well, it's a pretty easy story. At most 3 places we need to check for what are the largest and smallest values. I just wanted you to see where that comes from. So let's suppose we had our f of x was ax squared plus bx plus c, with a, b, and c are constants. Well, the derivative f prime of x would be 2ax plus b, right? And so if you try to do what I just said we should do, which is look at where is this undefined or where is it 0. First of all, undefined, not going to happen. You know, any x value at all, you could plug into that formula and you get some kind of number out. So no issues with undefinedness, but where is it 0? 0 is equal to 2ax plus b. Let's see. How about we move b to the other side? Yeah, that'll be negative b equals 2ax. And then finally, divide both sides by 2a. That's how they located that's really why the first part of the quadratic formula is negative b over 2a. All right, that's a great place to call it quits for the day. Hope you have a good rest of yours.